And as the State Association for Civil Engineers, Texas ASCE is happy to provide this service to you as members of the engineering community. If you don't happen to be a member of the Texas section or ASCE, we'd invite you to become a member and join in the benefits that you can get from being part of this professional association. Now I'm pleased to introduce our presenter for today's training, Mark Williams, PhD, PE, SE. Dr. Mark is a senior principal and managing director in the diagnostic group at Walter P. Moore. He's also the practice area leader for restoration and renovation, where he brings an inclusive and collaborative approach to repairing, restoring, and upgrading the built environment. Dr. Williams has 23 years engineering experience in diversified aspects of structural engineering analysis, design, repair, and management. He's been a member of ASCE since 1994. And now let me ask Mark to make his presentation. Mark?
Thank you for that introduction. And I'm assuming everybody can see the introductory slide.
Yeah.
Yes. Okay, perfect. So today's webinar is going to be on structural inspection and condition assessment of critical infrastructure assets. And by critical infrastructure assets, I'm talking about those assets that are vital to the operation of our infrastructure. That is, we need them in a very important way. So that's me, just to put a face with the presentation. I work for Walter P. Moore in Houston. I've had the, I guess, the pleasure of working on all different types of infrastructure assets, not only in Texas, but throughout the country, and even some international. And I'd like to share some of those experiences with you today. So as a framework for all of this, I'm going to use ASCE's 2017 Infrastructure Report Card. Many of you have probably seen this before, but there's a rating system for the various infrastructure assets. I'm going to talk about bridges, dams, drinking water, and energy more specifically. And I'm going to make comparisons between the report card on a national basis and the report card for Texas, so you can see how we're doing. But as you see what's scrolling along here, there are a lot of different pieces of infrastructure that we could focus on. In the 1 hour time slot we've got, pretty much have to limit it to something. And so I've selected 4 different areas to discuss, some good, some bad. In case you're not aware, the infrastructure grades for Texas look something like this. You have aviation with a B-, bridges a B, dams D, drinking water D+, flood control a D, highways and roads D, and wastewater D. So it's not exactly a flattering report card that you'd want to take home if you were a kid and you had to show this to your parents. As far as the agenda, we'll just touch briefly on critical infrastructure assets. Then we'll talk about what makes the grade that we're looking at here with these different letter grades. We'll talk about structural inspection versus condition assessment. They're actually 2 very different processes that feed into this. And then we're going to focus on 4 different types of assets: bridges, dams, drinking water, and energy. Like I said before, we could pick a whole lot more to focus on, but we do have an hour as far as the webinar goes, so we'll go with that. In terms of what makes a grade, this comes straight out of the ASCE report card. There's a lot of different criteria that go into the grading. You have the capacity. Does the infrastructure capacity meet the current and future demands? You have the condition of a particular asset. What's the infrastructure's existing and near future physical condition? You have funding levels. What's the level of funding being provided? Future needs. What's going to be the cost to improve the infrastructure? Will the future funding prospects address the need? You have operational maintenance needs, public safety, of course, resilience. What's the infrastructure system's capability to prevent or protect against significant multi-hazard threats and incidents? And lastly, innovation. What's new and innovative in terms of these assets? The 3 that I'll focus on today are condition, future need, and operation and maintenance. That's not to say the other ones aren't important, but again, we have a limited time frame to discuss. And as I'll get into a little bit here, in full disclosure, my background is in structural engineering, so I'm viewing these assets from a structural standpoint. There are clearly a lot of different angles that you can view these from a general civil engineering standpoint as well. So the grading scale, if you get an A, you're exceptional, you're fit for the future, fantastic. If you get a B, you're good, adequate for now. A C, mediocre, requiring attention. D is poor at risk. And if you get an F, you're failing, critical, unfit for purpose. So hopefully we don't want to have any Fs. We really don't want to have any Ds. We want to be making our way towards the As. Let me talk briefly about structural inspection versus condition assessment. So when I say structural inspection, we're talking about reviewing and documenting an existing structure. So it's featured in the photograph here. We're talking about a bridge. So this is the process of going out to the bridge with a team of inspectors, reviewing the conditions and documenting the conditions that you see there and quantifying those conditions. That information is going to be used later on as part of the condition assessment process to evaluate which bridges need to be repaired first. Typically, there are 5 types of inspection. There's initial inspection, which is when an asset is first constructed. There's a routine inspection. In the bridge world, that's every 24 months. That's just a standard general type of inspection that occurs on a recurring interval. There's in-depth inspection, which is a follow-up inspection. If something was flagged during a routine inspection, an in-depth inspection could be performed to look at a particular issue that was flagged. There's damage inspection, which is, as the name implies, if the asset is damaged in some way, you're going out to inspect it to see what the impact of that damage was. And lastly, there's a special inspection if there's a particular item of the asset that needs to be reviewed on a separate basis because of the condition. You could proceed that way. So I'm going to follow that framework throughout. We're not just talking about bridges. We talk about dams and drinking water and energy. These are basically the different types of inspection approaches that you could have. Well, let's contrast that to condition assessment. So inspection was going out and looking, evaluating, documenting. Condition assessment is all about management. And so condition assessment is a systematic collection of information, data of a structure with the intent of establishing a direct indication of physical performance, which can be used for costing and budgeting decisions. So now you have all this data from an inspection. What do you do with it? How do you prioritize it? How do you categorize it in order to make good, cost-effective decisions for the asset? So your management decisions could be development, evaluation, testing the new repair and maintenance techniques, corrective actions, life cycle cost analysis, project priority setting and scheduling, budgeting, funding allocation, and long-range planning. So again, this is all about the management of the asset. Inspection is about the evaluation of the asset. And I'll continue that theme as we go through the different types of assets. So let's talk about bridges. We'll do this one first. This is probably the one that you're going to be more familiar with than the other assets that are listed, but perhaps if you work in a particular area, you already know a lot about one of the different types of assets. On a national level, bridges get a C+. So that, how do you get a C+? Well, you have 9.1% of the bridges are rated structurally deficient, and we'll talk about what establishes that rating. But you almost have 10% of the bridges in the country being rated structurally deficient. If you're keeping track of the total number of bridges in the US, it's somewhere around 600,000. So you're about 55,000 bridges here are structurally deficient on a national level. So keep the C+ in mind. We move to Texas, good news, we get a B. So Texas is better than the average for the country, and I'll go into why. Chances are you've driven on a bridge somewhere in one of these TxDOT districts, probably many bridges, but this is just a representation here of how TxDOT is divided up, how it manages all the bridges in this state. Bridges can be on system or off system. It depends on whether the TxDOT manages the bridge or if you have local government managing a bridge. In some cases, there are also private bridges. So here's the good news. If you're in Texas, you have the largest bridge inventory. So I mentioned there are about 600,000 bridges in the US. 60,000 of them are in Texas. 10% of the bridges are in Texas. And the smallest percentage of structurally deficient bridges are in Texas compared to any other state. So 1.3%. So there's the good news. The two graphs below are plotting out between 2008 and 2018. That's the latest data that they have. the percentage of good or better bridges, so over the last 10 years, if you will, the percentage you notice has been going up. So if you started at 78.5%, now we're at 82%, a nice increase there. So 82% of the bridges are good or better in Texas. And we'll talk about what good and better are in just a little bit. If you look off to the right, it's just another way of showing this. It's over the same time frame, 2008 to 2018, this is the number of bridges. And so the boxes on the right, the purple SD is structurally deficient, FO is functionally obsolete, SSLO is just the loading is not adequate for the bridge, and the G and the B is good or better count. So you see that there's an uptake there in good or better. The amount of functionally obsolete bridges has remained relatively constant. It's dropped down a little bit there, and structurally deficient ones are hard to see at the very bottom, but there's not that many to count. Again, 1.3% in Texas. So pat yourselves on the back if you're in the bridge industry in Texas, because TxDOT has done a great job of maintaining the bridges. Doesn't mean we have to let our guard down. We still need to maintain them, still need to inspect them, still need to take care of all the bridges. They're only going to get older. But if you compare us to the rest of the country, we're doing quite well with bridges. This graphic is taken out of the Federal Highway Administration's Bridge Preservation Guide. It's a little bit grainy, but hopefully you can see it. And it's showing all the different beatings, if you will, that a bridge takes. You've got vehicles bouncing on the bridge, you've got water ponding, maybe you have de-icing salts, you have inadequate deck drainage, decay, misaligned bearings, surface corrosion if this is a steel bridge, you have scour, cracking in the columns, clogged debris in the expansion joints. All these factors are leading in and causing deterioration in bridges, and so you have to keep up with the maintenance process. So we didn't really have a bridge inspection program until we had this collapse of a bridge in 1967, which was the Silver River Bridge. And unfortunately, 46 people perished in this. And the underlying cause of this was stress corrosion cracking in the eye bars, which are shown on the left. So there was a little hairline cracking in there. It was actually hidden from view. Inspectors today, you can make the argument, may not have been able to notice this, just like that in the past. But the collapse of this basically was the cause of having federal oversight of our bridges. And so this created the Bridge Inspection Program, where bridges are inspected every 24 months. It established criteria for recording all of the information about the inspection into a national bridge inventory. Established criteria on the inspectors, team leaders, who's qualified to do inspections, and the program that you have to set up for bridge inspection. So this really kicked off all the federal guidelines that are still in place today. In that national bridge inventory, for bridges, they identified 3 different categories that need to be rated. And this is during the inspection process. So deck is given the MBI code number 58. That's the driving surface, your concrete slab. Superstructure is given the code 59. Superstructure are the beams that are supporting the bridge. And lastly, substructure at number 60 is basically the piers, foundations, or supports for the bridge. So these are the 3 main structural aspects for the bridge. There are other codes as well that we won't get into here, but these are important for the discussion. In addition, a condition rating was established. And so it goes from 0 to 9. A 9 is excellent condition for each one of these elements that we're talking about. 8 is very good, 7 is good, 6 is satisfactory, 5 is fair, 4 is poor condition, 3 serious, 2 critical, 1 imminent failure condition, and 0 is failed. When I took the bridge inspection training a long time ago, the way it was explained to me was no bridge ever gets a 9 because there's something wrong with it even when it's first built. And if you get a 0, that means the bridge is on the ground or in the water. And so everything else is somewhere in between. I'll draw your attention to the number 4, where it says poor condition, advanced section loss, deterioration, spalling, and scour. That is the dividing line for structurally deficient. That is, if any of the components of the bridge, that being deck, superstructure, and substructure, get rated as a 4 or lower, the bridge is deemed structurally deficient. That's not to be confused with functionally obsolete, which is a whole separate category. Off to the right, you see some common actions that are recommended. This is by Federal Highway Administration. If you're in the green category, the top 3 numbers, you would be in a preservation, a cyclic maintenance cycle. If you're in yellow, you're looking at condition-based maintenance. If you're orange and then going to red, you're looking at rehabilitation and replacement. So again, a 4 and lower is the dividing line for being structurally deficient. Now, as it turns out, the rating system is good, but it's not quite detailed enough. That is, there is one code for deck, one code for your superstructure, and one code for your substructure. So you can imagine a condition where if you were evaluating the superstructure, the beams, if there was one beam that was in bad condition, but the rest of the beams were in very good condition, you have to rate it based on the worst condition. So the entire bridge, all the beams get the same rating. Same could be said for the deck, same could be said for the foundations. And so it gets a bit skewed. If you have a localized condition, the rating is being applied all the way across to all conditions. So in response to this, AASHTO came up with what they call the commonly recognized structural elements, or CORE, C-O-R-E. And this is basically an effort to further subdivide all of the different structural pieces of a bridge and give them a more meaningful condition rating, so that you can sort out where the problem conditions are rather than having everything spread out across and assuming everything is of the same condition. So there's a guide that goes with this, which is the Bridge Element Inspection Guide Manual, that goes into great detail about this. But just to give you just a general sense of this, in the past you would have had deck, superstructure, and substructure. Now you have things like deck, girder, cap, column, abutment, and you can take this further and even categorize all the different types of beams, whether they're concrete beams, steel beams. So it adds more granularity to the inspection process rather than just having these 3 codes. Just of note, diaphragms are not in the core, as noted here, nor footings. They were excluded from there. So in this guide, they give you basically an example of all the different types of elements in a bridge. And so the one I'm showing here is element number 109, for lack of a better number. It is a pre-stressed concrete girder or beam. And what they're telling you is this is how you should go about denoting distress during the inspection process. So they tell you that distress should be measured in feet or meters if you're doing metric. And this is the different criteria that you might see when inspecting a bridge. So if you're looking at the beams, some of the defects you might see are spalls, delaminations, or patched areas, exposed rebar, exposed pre-stressing, cracks, efflorescence, which is that white staining that comes out of the cracks, and load capacity. And furthermore, they have established 4 different conditions. So this is in addition to the rating system of 0 to 9. Now we have a detailed rating system for each element. So if you're in condition state 1, chances are there's not much going on that's of worry. If you have cracks, they're probably hairline only. You get to condition state 2, you see there's some moderate words there, narrow. You get to condition state 3, you have severe spalling corrosion without section loss, medium size and density, severe with rust staining, and so forth. And if you get to condition state 4, you really need to take a more detailed look at this. So that's kind of a special category into itself. But basically, each one of these elements that we're looking at gets these condition states, and they are quantified. That is, if you find a certain length of beam has state 1, you document that. If a certain length of beam has state 2, you document that. So you have a nice inventory of what condition each part of the beams are in. To go along with this is straight out of the guide as well, is they help you define for cracking, crack density, efflorescence, spalling, delamination, patches, and so forth, what is hairline and minor, what is narrow and moderate, and what is medium and severe. So we're using these words correctly all the way from a hairline to severe in order to better quantify or qualify the conditions that we're seeing. So to put pretty colors to this, your condition states 1 to 4. If you're in condition state 1 for a particular element, it's nice and green. It's called good. And your common action for that would be a preservation or cyclic maintenance. Just keep an eye on it, maintain the bridge, keep the joints free of debris, and so forth. If you go to condition state 2, you're going to a fair category. So now you're in cyclic maintenance or condition-based maintenance when cost effective. If a particular part of an element is in condition state 3, it's considered poor. Now you're looking at condition-based maintenance, rehabilitation, or possibly replacement. So that could be replacement of a beam within a bridge, or replacement of the deck within the bridge. And lastly, if you get to severe, you're looking at rehabilitation or replacement. So that's pretty much the worst category that you can be in. All right, so that all leads up to the condition assessment process. So that was the inspection. We're not inspected. We looked for all these types of defects and deterioration, and we documented them. And we can even do it on a more detailed level for each one of these values of 1 to 4. Feed all that information in now to a decision-making process in order to decide which bridges you want to rehabilitate first. So that's where we get to condition assessment. So the figure on the right is taken directly out of the National Bridge Inspection Guidelines. And the criteria on the left is coming out of TxDOT. Since we're talking about Texas here, that'd be appropriate to show you what TxDOT considers in doing their condition assessment. And so the eligibility on this is in order for a bridge to be eligible for TxDOT's Highway Bridge Program, must have a sufficiency rating of 80 or less. So keep that in mind, 80 or less, and must be either structurally deficient or functionally obsolete. So it needs to be one of the two. So you say, well, what is the sufficiency rating? Well, it's complicated, but I'll try to boil it down for you on the right-hand side here. This pie chart is showing different criteria to look at in order to make this management decision. So first and foremost, sufficiency rating is the addition of S1 plus S2 plus S3 minus S4. You say, well, what are the S's? So if you look in the pie chart, S1 is up at the top. It's criteria number 1, structural adequacy and safety. S1 is 55% maximum. So in other words, the maximum score you can get in this category is 55. And this would consider things like the substructure, the superstructure, culverts, the inventory rating. It could consider the deck condition we talked about earlier. So basically think about this. You start at a 55. If you have any deterioration or condition states that are beyond excellent, you start to degrade that number. So it goes from 55 all the way down. It could go to 0 if you really wanted to, if it was a severe enough case. If you look over in the bottom left of the pie chart, you have serviceability and functional obsolescence. So this is about the use of the bridge and does it serve its current purpose, not so much as it's structurally adequate or safe. Two different things. So S2 has a max of 30. So the highest score you can get is a 30, and you simply subtract from there depending on the ratings. And it considers things like the lanes on the structure, the average daily traffic, the deck condition, the deck geometry, underclearance, and so forth. It's a long list there. S3 is essentiality for public use. How important is this bridge for public use? So I started out saying critical infrastructure assets. Is this bridge critical, or is it going to be a complete nuisance if you have to detour around it? How long is the detour length to get around this bridge? You can imagine some of these bridges in the state are very, very important and difficult to bypass. So you add up S1, S2, and S3. So your max score here of 55 plus 30 plus 15, you could get a perfect 100 if you met all this criteria. There's a special reductions category down at the bottom, and that considers things like the detour length, the traffic safety features, the structure type. There's a maximum deduction of 13. So in theory, you can get an 87 if you had full deductions, even though you had 100. So again, S1 plus S2 plus S3 minus S4. The highest score you could get is 100. The lowest score you could get is a 0. And that's the way decisions are made right now. That is, there is a ranking based on sufficiency rating. And if the bridge is structurally deficient or functionally obsolete, it's going to fall on this list. And you can start ranking and prioritizing which bridges that you want to address first. I'll pause here for just a second. So what I would like to do is we have 3 more critical infrastructure assets to talk about. I'm going to follow the same methodology. I'm going to bring it all the way through to the different ones. The bridges have the most well-established criteria for evaluating them and for condition assessment and making decisions. So I think it makes sense to try to extend that on to the other ones where there isn't necessarily a fully developed program in place. So I'm going to use this as a demonstration as we get to the other types of assets. All right, so that's bridges. The next one is dams. So if we look at the National Report Card, we find that dams are a D. Why are they a D? Well, there's 15,498, 17% dams identified as high hazard potential. So this is not good that we have dams in this condition. Now, by way of comparison, that's the national grade. Lo and behold, the Texas dams are the same. They're both Ds. So this is a good case study here of we are at the national average on this. It's a D, it's not a good grade. And clearly there's a lot more that could be done with this particular type of asset. So I want to show you loss of life and property damage. This is from 1963 to 2006. It's kind of an interesting range. And I show you this, there's only one Texas dam on this chart. And there have been failures, more so than just the one that's shown here. But I want to show you what the ramifications are of dam failures. And so if you look down the list, I won't go through all of them, but you see like 546 houses destroyed, 771 houses destroyed, 18 bridges destroyed, 117 businesses, 108 houses damaged, and so forth. You see the amount of damage. It's not necessarily the number of lives lost. Of course, that's critical in all of this, but there's a lot of collateral damage as well when you have dam failures. The one Texas one that is on here is the Nix Lake Dam. This is 1989. It listed one life lost and unknown damages, so I'm not quite sure what exactly that means. But you can see they're pretty much spread out throughout different states in the country. So let's focus the attention on Texas. So this is the state program statistics. This is 2018. Much of the tracking and program management for dams in the state falls under the purview of the TCEQ, which is the Texas Commission on Environmental Quality. This is their map showing all the different dams and their locations within the state. As far as state regulated dams, there are 4,014. 1,409 are considered high hazard potential. 335 are considered significant hazard potential, and 2,270 are considered low hazard. So on staff for the TCEQ is basically 27 people trying to manage dam safety in the state with a total budget of 1.6, almost $1.7 million. It's not a lot of money, and to spread out that management across the entire state. As you know, it's a very big state. I think one of the most telling statistics with dams is in the history that they've been tracked in Texas, there have been 300 dam failures. Half of those have occurred in the last 9 years. So out of the 300 that have ever occurred, half have occurred in the last 9 years. Some of that is a consequence of Harvey, but not all of it. And dams take on many different types of sizes and forms in the state. They can be earthen dams, concrete dams, and so forth. But that's pretty remarkable that half have failed in the last 9 years. And that should definitely gather some attention for you. I put earthen dams up here. I'm not going to talk about it in great detail, but I want to acknowledge that there's a good portion of dams that are earthen. And so basically this is a nice illustration of showing what that type of construction looks like. You have an embankment fill, you have a center core, you have water behind the spillway, you have a certain amount of freeboard so the water doesn't go over the dam, and various other parts that are illustrated here. This illustration is provided by TCEQ in their guidelines for operating maintenance of dams. The one that I would like to spend more time on are the concrete gravity dams. Again, this is an illustration from TCEQ in their operations guide. Gravity dams are concrete construction. They don't have to be solid, although that's what's depicted here. And you'll notice by way of the figure, the arrows that are shown here, this is how it sort of resists all the water behind it. You've got this pressure from the reservoir behind there. That resistance is offered to movement by the abutment, which is the end of the dams. There's resistance to movement offered by the key and the foundation. And then there's resistance, it's basically friction underneath that keeps it from sliding. And so that you can imagine these are fairly massive size structures that are in place in order to hold back all that water. Now, I mentioned before that if you look at the bridge world, they have well-established guidelines by the federal government for how to inspect, how to do a condition assessment, and so forth. As you progressively get to other types of assets, there's not really an organized federal effort to inspect and evaluate, and a lot of those decisions are made either at the state or local level, and sometimes even made by the owners and operators of dams. This particular flow chart here is provided by TCEQ in their guidelines. And we're going to focus mainly on inspection, which is the top box. But I wanted to show here that there is actually a process in place. So it starts with inspection, then you go to repairs and maintenance, you go to an operation and a monitoring mode, and you repeat this process depending on the frequency of inspections and the repair cycle. And there's a detour down at the bottom for emergency action. When it comes to bridges, when it comes to dams, unlike bridges and other types of assets, it tends to be more scenario driven as far as what to do. And that scenario is based on risk. And so if this event happens, we should do this. If this event happens, we should do this. And so there's a lot of scenario planning that occurs trying to prevent catastrophic failure of dams. The challenge too with dams in this state, and this would apply to other states as well, is the majority of the dams are not owned by a municipality or the state. So where like bridges, you have TxDOT owning a lot of the bridges, or you have county or city entities owning the bridges. In the case of dams, 60% in Texas are privately owned. And you can imagine with private ownership, sure, they want to do the right thing and they want to keep their dams safe and they want to inspect them and all that, but there's a lot of constraints on them from a financial standpoint to do all these things. They may not have the staff and resources in order to keep up with the inspection program. So let's look at an example dam. And it's important in the inspection process, the first thing you need to do is identify all the different structural elements that make up the dam. So just like with bridges, we had deck and superstructure and substructure. Let's take a dam, for example. Let's label the different structural parts. So up at the top, we'd have parapet walls. We would have gates at the top of the spillway. There may be a bridge going across the top, piers supporting the bridge. There's a sluiceway that allows water out, a principal spillway, buttresses in this case. This is a buttress dam. And the abutments are at the ends of the dam that are helping to prevent sliding from occurring. This dam has a powerhouse, so a lot of dams are used to generate hydroelectric power. And you can't see because it's submerged, but you have a stilling basin down below. A couple things about this dam in particular is, one, we're only seeing part of the dam. That is, it's very hard to photograph the whole thing unless you're pretty far back. So you're seeing one spillway. This dam has 3 spillways. And this dam is not solid. It is actually hollow inside. It has buttresses as part of its support. And dams, by way of function, are not intended to be overtopped. That is, they have mechanisms in place. They have gates up at the top to help release water. But their primary use is not to overtop them. That is, you want to direct the water in a controlled fashion down to a powerhouse or other methods. Have a controlled release of water. You don't want to be in a situation where they're being overtopped. I mentioned all the dam failures that had occurred in the last 9 years. A third of those failures were overtopping. So if you can imagine back to Harvey in 2017, we were very close to that situation with the Adequacy and Barker Cypress dams. They were getting very close to being overtopped, and they went ahead and did a controlled release of that water in order to prevent any further damage to the dams. So once you have your different structural elements identified, you proceed with the actual inspection process. So here's one scrappy engineer here that's rappelling down the spillway. And notice a couple things. There's plant life growing out of the cracks, but there are cracks in concrete. And this engineer is documenting distress that's seeing to the different parts of the dam. So when I say distress, it could be concrete cracking, spalling, could be efflorescence, exposed rebar, corrosion, the types of things that concrete deterioration. And one thing of note in an inspection process like this is we're not necessarily looking at global stability of the dam. We're looking up close at all these different elements, but we need to remember that the dam itself is a very large rigid block. And so you have to look at the abutments. You have to look at, by way of survey, whether the dam is moving or not from a global stability standpoint. But in this particular photo, we're looking at the spillway, documenting different distress that's occurring. You can see the powerhouse in the background down below, and there's a little bit of release of water there. After the spillway, looking at the buttresses. So you can look at the size of the buttresses here. This is compared to a person. Actually quite large. I mentioned before this dam actually is hollow. So you're seeing the exposed buttresses in this particular case. There's actually more to be seen inside the dam. And so you're looking for the same type of conditions: cracking, spalling, deterioration, corrosion of reinforcing steel, any type of compromised structural support for the different elements. And you're documenting these particular conditions that you're seeing, because that's going to inform the condition assessment process when you're done with the inspection. On the inside, you might see concrete spalling, delamination. This happens to be at the edge of a buttress on the inside. As you can see, the corrosion activity, reinforcements causing concrete to spall and delaminate. Or you might see exposed reinforcing steel. It's not a particularly troublesome condition, but worth documenting. You do notice there's some water infiltration through cracks as well. So for each structural element that we talked about, whether it be the spillway or the parapet walls or the bridge up above, you can document the condition of that and record it. And you can do it much the same way that it's done with bridges. That is, this table shown here would allow you to have an element description, a primary member. So for example, the spillway, you could have spillway 1, 2, and 3 if you'd like. And for each one of those elements, you would go down the list here and you would identify what type of defects did I see in that particular structural element. Did I see cracks, spalls, delamination, efflorescence? Is there a concern about load capacity? And I would quantify in each one of the condition states what I saw. So if I saw some isolated and hairline cracks of a particular length, I would put them in condition state 1. If I saw narrow or low intensity cracking, I'd put it in condition state 2. If I saw medium size, high intensity cracking, I'd put it in condition state 3. And if I saw something really troublesome, maybe some very wide cracks or a lot of water coming through the cracks, I would go to condition state 4 for that, and I would quantify the length of cracks. Same thing can be done for spalls, efflorescence, and looking at the load capacity. I didn't mention this earlier with the bridges, but the letters denoted down at the bottom are for the cause. So if you think you know the cause of the cracking, you can document that during the inspection. So UN is unknown. I don't know the cause, so therefore UN. CO would be corrosion, if you think it's related to corrosion of reinforcing steel. And DE is design. So if you have some concerns about load capacity, that is, you see something deflecting in a large amount, or you have some concerns about how much load it can carry, you could mark that as being DE for design. To go back and review the design and make sure it's adequate. And there's a little bit of room at the bottom, just blank space where you can have additional commentary for the condition states. So you would do this for each of the elements in the dam. So the parapet walls, the spillway, the bridge, the parapets, and so forth. And you would collect all that information, and that's going to inform the condition assessment process. So if we use the same model that we use for bridges, here's the pie chart again, and just for demonstration purposes, we're going to keep the same percentages. So we're going to have a condition rating, and it's going to be the summation of S1, S2, S3, and we're going to subtract off S4. So as a reminder for you, S1 is your structural adequacy and safety. So let's just say maximum score of 55. This is where you weigh in the condition that you saw for the buttress, for the abutment, for the spillway, for the parapets, piers, gate, basin, whatever the structural elements are that are identified in the dam, and it's a weighted average with the maximum score being 55. So if everything was in excellent condition, you would get a 55. If there are particular parts of the structure that are subtracting off of that, you'll get less than 55. If you move over to serviceability and functional obsolescence, maximum score of 30 just for demonstration. What are some of the serviceability issues you would see and functional issues? Well, you could have cracking. The concrete cover could be particularly low, so it's exposed and reinforcing. There could be issues with the joints in the dam. You might see excessive deflection, issues with spillway, powerhouse approach. Is the powerhouse not adequate anymore? The spillways not adequate for their purpose, a number of different things, and the approach, which is leading up to the dam. And lastly, number 3, which is RES3, essential for use. So is this dam being used for power production, water supply? How important is the dam as a critical infrastructure asset? That is, if we took the dam offline, didn't have to worry about it at all, would everything be okay? Or does it serve a very vital purpose? And also along that lines, is it safe for operation? So if you were to add these up, 55, 30, and 15, you'd get to 100. And then you take your special reductions. So if this is a particular structure type that, let's just say, has been known to be problematic or is outdated, you might take a reduction for that. If there are certain safety features that need to be in place that aren't, or it needs to be brought up to the current safety standards, you might take a reduction there as well. So you would start at a perfect score of 100, you might take 13% off, you'd be at 87. So a perfect 100, no issues. A 0 is critical condition, but it gives you a way of ranking, prioritizing as you go through this particular dam as to how important it is to maintain and repair it. I mentioned before, under the purview of the TCEQ, you have about 4,000 dams. Total dams in Texas about 7,000. So you can imagine we need a system in place here where we can at least rank and prioritize these in order to get a handle on which ones need to be addressed first. Otherwise, we're kind of at a loss. So if we're at a D right now, how do we get ourselves above a D? How do we get ourselves to a C, B, and up to A? We need some type of prioritization ranking system and be able to make some management decisions in the condition assessment process. Okay, and so that's dams. So we're doing a very quick, broad brush review of these. Let's move on to the third one, which is drinking water. So nationally, drinking water gets a D, and one of the main drivers on this one is that 6 billion gallons of treated water is lost every day. So ASCE is viewing this, at least this particular statistic here, in terms of water quality, water loss. Again, my bias is a structural engineer. I'm looking at other parts of the process that I'll get into in just a minute. So they nationally get a D, Texas gets a D+, just barely ahead of the average. And so let's look at a water treatment plant here. This one happens to be emptied because you need to perform an inspection on it. And so there it is, drained. You can see some corrosion product on some of the baffle walls, but all the water's been removed, so you can go about doing the inspection. You can see ladders on the right for getting down into the tanks. This happens to be one of the flocculation tanks as part of the water treatment process. So water treatment, water quality is very important, but if the tank is not structurally sound or has issues, then that's equally important, if not more. That is, it's not going to be able to function. If there are structural issues in the tank, you won't be able to use this plant, and then you are taking away a critical infrastructure asset. Everybody has to have clean, treated water. So just like the other assets, the inspection process starts by identifying all the different components to be inspected. So they're labeled here. So if I start at the bottom, you have a basin slab, you have basin walls that form the tank for this particular area. You have a support column, you have a rake arm, that's what's spinning around and churning the water as it's being treated. Up top, you have a drive platform, railings, and baffle walls, basically demising walls separating the different tanks. And so you're going to do, just like before, a condition rating process for each one of these elements, and then that's going to feed the condition assessment process. So just give you a sense of this. So if you drain the water and you look at this, you can see quite a bit of scaling that's occurring on the walls. You can see cracking in the walls. These happen to be through thickness cracks. You can't tell from here, but we know that by way of investigation. So you've got cracks all the way through the walls, and you have a lot of concrete that is eroding or scaling off of here. If we were to sort of cheat and fast forward and look at the repair process of this, you'll notice that there's been quite a bit of concrete removal in the walls, and you can see just a hint of it just up above in the beams there. This construction worker is placing shotcretes. It's basically casting back concrete in order to fill in those voids. This is one of the walkways. This is the amount of deterioration that's occurred that the entire walkway had to be removed. As you imagine, if you're in a water treatment business, you use chemicals in order to treat the water. Those chemicals aren't necessarily very favorable to reinforcing steel and concrete. And so there have to be protective coatings and durability measures in place. Sometimes it still gets out of hand. And so in this particular case, the entire walkway had to be removed and replaced because of the amount of deterioration. So that would have been picked up on the inspection process. The deterioration would have been probably at the point of removal, it would have seen that it was actually much worse than you could see visually on the surface. But nevertheless, this would be an item that would be flagged and identified for future evaluation and possible repair. So you would go through each one of these elements in the treatment plant, and you would assign condition ratings to them. So just like what I showed before, in this case, this is a concrete structure, so you're going to have cracks, spalls, delaminations, efflorescence. Perhaps you have issues with load capacity if tank walls are deflecting. And you're going to rate based on condition state 1, 2, and 3. And if it gets beyond that, you're going to have condition state 4, which is you're going to have to do additional testing, non-destructive evaluation, laboratory testing, and so forth to try to characterize what's going on. But you're going to quantify for each one of the items that we saw, the basin slab, the basin walls, the railings, you're going to quantify the condition of those. And then that is going to be used to inform the overall condition assessment process. So you would have a table for each one of the elements that we're going through. I followed the same format as I did before. Here's my condition assessment. So S1 plus S2 plus S3 minus S4. The only real difference here is the items that you're looking at. So a structural adequacy and safety, a max score 55, just for example. This time the elements are the basin slab, the basin wall, the support columns, the rake arms, the baffle wall, the driving platform, the railings, and anything else that's structural that you could come across. Serviceability and functional obsolescence. In this case, cracking is very important in tanks. Concrete cover joints, the tank capacity. Maybe the tank doesn't have adequate capacity anymore, so it's functionally obsolete for that reason. Or the chemical processes that are used perhaps aren't conducive to the tank. And then for essential use, maximum score 15%. This is obviously for the water supply. Chances are it is going to be critical that you have treated water. It is possible that some plants serve a secondary purpose where they're not the primary for water treatment. But more than likely, it's going to be a critical, because if it goes down, then you don't have treated water. And lastly, special reductions, 13% just for demonstration. The structure type and the safety features that are in place, you may have reductions for that. So you sum all this up, S1 plus S2 plus S3 minus S4, you come up with a number. 100 is perfect, 0 is critical, and you establish a threshold where you would take action. It also allows you to rank them by priority. So which one of these water treatment plants or tanks is the most critical in terms of addressing. So it's a systematic procedure, just like would be applied to dams, just like applied to bridges. All right, so we're in the home stretch. The very last one I'll talk about is energy. If you look at ASCE's report card for the nation, they give it a D+, which is not very flattering. And one of the primary metrics for that is 3,571 total power outages reported in 1 year. You notice in their graphic here, they show these hyperbolic cooling towers. Those are actually not common in Texas, but they tend to be associated with nuclear power plants or coal-fired power plants. You can visualize, if you want, Homer Simpson sitting in the control room at the nuclear plant as an example. When you get to Texas Energy, interestingly enough, there is not a grade. And I haven't dug down far enough to understand why. It's probably because there's not enough information reported. It's not that anything is critical here, but we just don't have enough data to go by. In Texas, you do have alternative energies. You have the wind turbines, you have solar, and then you have quite a bit of conventional energy generation, which would be your power plants. And so speaking of power plants, let me touch on a critical infrastructure asset of a power plant, and that is cooling towers. So cooling towers are providing the cooling of water for a process that involves steam generation. So your coal-fired plants, nuclear plants, similar to that, also used for chemical process as well. This is very much like the radiator in your vehicle. So if you cannot cool the water coming out of the plant cannot run. So it's an absolutely critical element to have. It's generally placed out in a field somewhere and nobody really wants to worry about it, but it is critical to the operation of the plant. if I'm a steel, if I get steel cooling towers, they're very susceptible to corrosion. And so if you see the photos down at the bottom, particularly the one in the center, the supports for this cooling tower can be completely eaten away. There are certain chemicals used in cooling towers in order to treat the water, and those chemicals are very harsh to the structural members. If I'm talking about concrete cooling towers, I have the same type of deterioration that we've been discussing all along. It's a pretty cool looking cooling tower here. If you look in the bottom left, that is actually post-tensioning strand there that is fractured and failed, and there's also reinforcement next to it, both of which are corroded. Bottom center is corrosion and spalling of concrete, and on the right you have a bearing support that is being compromised by corrosion and deterioration. Same approach applies here. So for cooling towers, I can identify all the structural elements. So in this case, I've got them labeled. You've got louvers, exterior columns, ring beam, basin walls, fan shroud, hot deck, interesting terms that they use for cooling towers. So each one of these elements can be evaluated during the inspection process and given condition states between 1 and 4. If you look in the inside of a cooling tower, just as cool as the outside, I suppose, you also have structural elements. So you have columns, you have pedestals, you have a basin slab, you have a fan deck floor at the top, fan deck beams, a fan opening, and a fill structure. That's where the water actually does the cooling. All of those items can be individually inspected and given condition ratings. And so if you were to do that on an element by element basis, you could use the same methodology here. So here's an example. This happens to be for a fan deck precast planks. What are the types of distress you might see? Cracking, spalling, delaminations, efflorescence, load capacity, perhaps it's sagging. You want to evaluate the load capacity. And for each condition state, you could rate that particular element. How much of it is in state 1, 2, 3? Does it need further evaluation in condition state 4? There's a separate table on the right that helps guide you. So if you're talking about cracking, what is hairline, narrow, and medium, the crack intensity, spalling, delamination, efflorescence, etc. All of those things can be listed out and given condition ratings in order to evaluate the asset. I'm showing a table here that can be used for condition ratings. So if you were to break it down just by element, you could simply assign the rating codes to each one. So whether you're talking about the louvers, or you're talking about the ring beams or the columns and so forth, they could all be filled out in this sort of convenient, handy inspection table. And you'd quantify everything over on the right, which are the conditions states 1 through 4. And lastly, following the same model here, structural adequacy and safety, you have the different structural elements of the cooling tower: basin slab, basin wall, louvers, ring beam, support columns, hot deck, fill structure. The serviceability and the functional obsolescence is cracking, concrete cover, joints, deflection, maybe the chemical process that's being used, and the overall operational control of the tower. Essential for use, item number 3, power production or process cooling. How critical is this cooling tower to the operation of the power plant? It's obviously very important. Some can have portions of them shut off while the other cells still work. But if you have any loss of structural support for a cooling tower, you effectively cannot run that part of the power production. So it's critical to provide power to the infrastructure. And lastly, special reductions, just 13% for argument. Structure type or redundant features that the cooling tower might have, like being able to close certain cells while other ones are being operational. So again, add it all up, S1 plus S2 plus S3 minus S4, come up with a condition rating, establish a threshold for what is acceptable, and you can also rank everything as what's most important to maintain. So we're getting close to the end of the hour. I did want to leave you with this. This is a mapping of the grades that have occurred in 2004, 8, 12, and 17, just so you can see the progression of things. You will note that things are by and large getting better, not worse, which is a great sign, but still the grades serve to raise the awareness here that a lot more funding needs to occur for infrastructure to get it where it needs to be. And with that, I will go ahead and wrap it up. How do I see if we have any questions?
Mark, thank you very much. I will read some questions to you. There are several of them. The first one is, Can I use the FHWA condition assessment for the water wastewater infrastructure?
Yes, and so the process that I've showed is not formalized in any way by FHWA for water treatment, but the process can be the same. That is, you should be able to take everything that's been developed for bridges, you should be able to transport that to water treatment plants.
The next one is life cycle cost analysis for bridges can be complex. Also, any decision making for bridge replacement repair should consider social economic effects on surrounding communities. Both can take considerable time, and timely decision making is important. Your input on this issue would be appreciated.
I guess that question is summarizing it very well. Yeah, there's a lot of factors that play into this and policy decisions. I'm not going to pretend to have the answers to that, but I think it's important to say how complicated or complex the issue is. It's not as simple as just giving a rating and a ranking. There's more that plays into it.
This one is a statement. The Texas dam inventory includes U.S. Army Corps of Engineer dams being overseen by U.S. Army Corps of Engineers. Any comment?
That's true. And there are, I'll say, regulatory guidelines or operational guidelines out there from Army Corps, as well as other entities helping to oversee dams. I think the intent is certainly there to help monitor and keep dams safe, but it doesn't have the full, I guess, or widespread regulation that bridges have, for example.
The next one is, how do we categorize the intensity of cracks?
So I showed tables basically indicating the width of the cracks. And so it could be anything from hairline to what could be severe would be something on the order of maybe a quarter or half an inch or even bigger. So it's generally done based on width for cracks. They're flagged, and then there could be additional follow-up and in-depth inspection if needed, if there was a concern about structural integrity from those cracks.
Okay, and the next one. Sometimes there are invisible damages that might show up during the rehab and repair process. How do we reflect that on our initial rehabilitation and repair budget? Maybe as a contingency percentage or something else?
Yes, good question. Certainly, when you get into the repair process, you tend to find more than you think. That's not, everything is not visible on the surface. What's commonly done is to use a multiplier. That is, just for sake of argument, if you had 1 square foot of concrete to be repaired, you would probably multiply that by an additional 30%, maybe 50%, maybe even 100% to account for what you can't see. And that would also account for ongoing deterioration while you're in that process getting ready to repair. So you certainly need to escalate the repair quantities. As far as hidden and undiscovered conditions beyond that, you basically have to deal with them as they arise. So a contingency for that is probably the best way to go.
Okay. Are you seeing an increase with the utilization of technology for these inspections, such as UAS, drones, ROVs, and submersibles for under the water level? If so, how well are they being received?
Good question. And there's a lot of this experimentation going on in different states right now. Drones is probably the most common one that is getting the attention. As far as I know, you are restricted from flying drones over bridges. That is if they're active roadways. They can be used on the sides and underneath. The lighting condition is not always the best for using drones, particularly if you're shaded underneath. So it still requires some human effort. But I think we're definitely going that direction. Probably more so using technology to screen first, or pre-screen if you'd like, and then having humans go in and actually look up close at things that are flagged.
Could you mention the codes again towards the end?
Could I mention the codes? I'm not sure which codes the question's referring to.
it says towards the end of your talk.
Codes.
Maybe those codes, were they the unknown? And
Oh, talking about these?
that's what I'm wondering if they mean the CO
Okay.
and the
Oh,
DE.
I'm thinking like design codes.
Yeah,
Yeah.
that's
So
true.
the UN, this is the cause. So when you're inspecting, you can denote what you think caused the particular defect. So UN is unknown. That is when you're inspecting and you don't know the reason you would put UN. If you suspect that it was caused by corrosion or reinforcement, which in concrete structures, that's very common, you could indicate CO. If you're seeing a potential issue with load capacity, that is something is deflecting too much, you would indicate DE for design. That is to flag it, to go back and look and make sure the design is adequate for that particular member.
Mark, they further clarified here. They said codes mentioned regarding dams.
Oh, codes regarding dams. So you have the, I could probably go back up to it. You have the Texas Commission on Environmental Quality has their guidelines for operation and maintenance of dams. That one is particularly helpful document to look at. And I would say start there for Texas.
Okay, we have a few more. The Texas energy grade was not provided this last report card cycle because it did not change from the prior grade given in the prior report. I believe it was a B or maybe even a B plus, so it was also not considered a problem area.
Thank you for that clarification. That would make sense if they didn't list it, although I guess a counter argument would be in 2004, 8, and 12, they had the same grade of B plus and they listed at that time. So you will note that not only energy, but there are other categories that weren't listed as well. Ports, hazardous waste, schools, solid waste, and so forth.
NDE is not used currently in routine bridge inspections. Mainly visual inspections may not be sufficient to assess the overall conditions. Any thoughts?
That's true. So a routine bridge inspection, which is done every 24 months, is typically just visual in nature. However, items are flagged that are of concern, and in an in-depth inspection, which would be a follow-up inspection, NDE is commonly used to further investigate.
I've got three more and then we'll...
Okay, I like this. We got lots of questions.
Yes, rapid fire here. Why are the levies not being evaluated? Texas has a lot of levies.
Good question. Good question. I don't have an answer for you on that one.
Suppose there are 5 girders to a bridge and one of them has poor serviceability criteria and the other 4 are in good condition. In this case, you mentioned that the guidelines are not very detailed and would consider these cases going by worst condition element and not the overall bridge condition. But here you mentioned this approach would need improvement. Why? Do we need to classify the condition of the bridge going by the most critical element?
The way that the procedure is right now is that the condition rating is still done on a 0 to 9 basis for deck, superstructure, and substructure. However, in the inspection process, the additional condition ratings, that is the 1 to 4 categories, are recorded. And so that is part of the inventory of the bridge now. So if a particular bridge has that issue where because one beam is bad, all beams are deemed bad, you do have that backup documentation showing which beam it is. That lets you go a little bit more granular now with the decision making on what to do for that bridge, rather than just giving it a broad brush and saying the entire bridge is deficient.
How about water mains and similar buried assets? CCTV makes it more challenging than for other infrastructure.
Yep, very true, very true. And it's not in ASCE's report card, but you could make an argument it should be.
Okay, and let's see. Well, we've got some thank yous in the chat, which we appreciate, and I sure want to thank you, Mark, for such a good presentation and very clear, and your quick responses to a number of questions. So also thanking all of the participants who listened to Mark's structural inspection and condition assessment for critical infrastructure assets today with us. Each individual registrant will receive an attendance acknowledgement without any further action, with the one continuing education professional development credit. For those that are attending with the group, the site coordinator will receive it, and the attendants will handle it for distribution to those who participate. If you're interested in presenting a webinar through the Texas section, please contact A. Salazar, ASALAZAR, at walterpmoore.com for more information. You can also visit the webinars page on the ASCE Texas section website for a full listing of upcoming sessions. The webinars, we have the next 3 are scheduled June 9th, July 14th, and August 11th. And we're always available for any questions and comments, and hope to hear from you soon. We appreciate all the wonderful comments that you've given on the chat to Mark for the wonderful session, the very clear presentation, awesome, etc. Mark. So again, thank you very much.
Thank you.
And you're well appreciated. Turning it over to Mike to close out the session.
All right, just echoing Bob's statements. Thank everybody for joining us today, and have a great rest of your day.